Thank you, Alexander, and thank you to Lead for the clear presentation. I have to thank them for getting me up to speed with the co-heating test more than 2 years ago. Today I would like to present the work which we've performed in the framework of a collaborative project between KU Leuven and Knauf Installation. And I would like to talk today about the state-of-the-art on the co-heating test methodology, where I primarily focus on the co-heating test analysis, so analysis of the measurement data. So as already mentioned today, we see that more often than not the actual energy performance of buildings can differ significantly from the predicted energy performance of buildings. So we know that the energy performance depends on 3 factors. First, we have the building fabric, so the materials that make up the fabric of or the envelope of the building. We have the installed surfaces with their inherent efficiency. And we have user behavior. That is, users are not easily controlled, so they will also have an influence on the energy performance. Today, we will primarily focus on the building fabric, so the characterization of its thermal performance as an important first step towards assessing the energy performance of buildings on the basis of measurements. And the co-heating test is an important or a common test used to characterize this thermal performance. Here I show you a co-heating test setup in an investigated dwelling. So you can see the heaters that are dispersed throughout the dwelling to heat up the indoor environment. They are controlled using thermostats. We also have ventilators to mix the indoor air to have an as homogeneous distribution of the temperature throughout the dwelling. And at last but not least, we have the sensors spread throughout the dwelling to monitor the variables which will serve as an input for the data analysis. This scheme on the right shows the basic principle of the co-heating test. So it is actually a quasi-stationary test. Stationary because we keep the indoor air temperature to an elevated level, for example 25 degrees. So we keep it at that level using the heaters and ventilators spread throughout the dwelling. During and then still we have the weather conditions. So we have stationary conditions inside, but we have the dynamic weather conditions. So that explains the term quasi in front of the stationary. During the test, we monitor the heating power, the heat input to the indoor environment. We also measure the indoor temperature in the different zones of the dwelling. We measure the weather conditions, so we measure outdoor air temperature, the precipitation, wind speed and direction, and solar radiation. Important to note is that we monitor these weather conditions and other inputs quite in a detailed manner, but as a basis for the data analysis, we aggregate this data to, for example, daily averages. The most important results of the co-heating test is the overall heat loss coefficient. This coefficient groups the transmission heat loss and the ventilation heat loss through the building fabric. So here I show you the basic heat balance which is assumed during any co-heating test. So what we do is we relate the heat which we need to input to the indoor environment to the temperature difference which exists between indoor and outdoors, and the heat gains which we get from solar radiation. But first I would like to briefly take a brief detour to show you some of the physical phenomena which work behind the scenes of this simplified heat balance. So we assume that the building acts as one zone. And we also do quite an effort to make it such a way. We, as said, we disperse the heaters throughout the dwelling and to get a stable elevated temperature in all of the rooms of the dwelling. The indoor temperature, as said, is thermostatically controlled, and we aggregate the performance data to, for example, daily averages. For now, we assume the thermal mass to be in equilibrium. There are some cases in which this is not the case, but we will come back to that later on in the presentation. So we can assume a stationary heat balance towards the indoor air. I've written it down here. I've written down all of the terms we can distinguish here. So you have the heating power which we put into the dwelling. We have an additional heat gain due to solar radiation coming in through the transparent parts of the fabric. We have the transmission heat loss through the building fabric. As we saw earlier in some slides earlier, we saw that the transmission heat loss is described as a function of the temperature difference, or the difference between indoor and outdoor air temperature. But in reality, the transmission heat loss is actually dependent on the surface temperature differential. So to correct for this, I've included in this equation correction terms for solar radiation and for long-wave radiative heat exchange with the sky. I will return to this matter in 2 slides. Then we still have the ventilation heat loss through the building fabric, and a latent heat loss which is attributable to, for example, drying out of building moisture. Let us zoom in on the building fabric. So here we see the connection of the window to an opaque fabric part. So first we'll consider the opaque part at the top. So as said, the transmission heat loss through the building fabric depends on the surface temperature differential. In the coheating analysis, we assume the transmission heat loss to be dependent on the temperature difference between indoor and outdoor air. So we have Ti and Ta, but in reality, the outside fabric, the outdoor surface of the fabric, can be heated to higher levels due to solar irradiation, but it could also be lower than the outdoor air due to radiative heat exchange with the sky. The same goes for transparent parts, so there also we can have undercooling due to this radiation exchange with the sky. Direct and indirect solar gains through transparent parts are taken into account into a separate term in the heat balance. Additionally, we also need to take into account the thermal lag. Thermal lag can be introduced by the building fabric. So, for example, the heating power which we need to deliver during one day might also be influenced by solar radiation that has been charged during a previous day. So it makes sense to relate the heating power at the current day with a kind of weighted average of solar radiation and temperature difference inside-outside of the current day and a previous day. So all of the earlier considerations lead us to write down this rather complex-looking heat balance. I will not go into detail here because it will lead us too far. The most important thing that we take from this is that there are a lot of physical phenomena that work behind the scenes, and having written this down can help us interpret the results of the coheating test later on. Let us turn to the linear regression, which is used as a basic analysis tool with the coheating test. So as said, we have a simplified heat balance, which we assume to hold during the coheating test. So it's a stationary heat balance, and we have aggregated performance data as input. So for example, we have daily averages of the heating power, the temperature difference, and solar radiation as variables. You see that there are quite some simplifications which we need to introduce to go from the more complex equation to the simplified heat balance. And all of these simplifications are statistical in nature. So they all we have actually quite crude performance data available as a basis for the coheating test analysis, and the simplifications all result from this fact. I will not go into detail in all of them, and I will turn to the linear regression analysis. So to estimate for example, the heat loss coefficient, which is the most important parameter, and the solar aperture coefficient, we need to apply linear regression, assuming this equation and assuming the collected measurement data. Three options present themselves here. We have first we have the simple linear regression on the basis of the equation on the right, on top of the graph. How do we get to this equation? We actually make an assumption on the solar aperture coefficient, and we take the term, the solar gain term, to the left-hand side of the equation. This way we can relate a kind of solar corrected heating power to the temperature difference between inside and outside during the test. The sole result of this simple linear regression is then the heat loss coefficient. And an advantage of this method is that it is easily represented in a two-dimensional fashion. So you see the graph where we have on the y-axis the solar corrected heating power, and on the x-axis we have the temperature difference inside-outside. The heat loss coefficient is then determined from the upward slope of the regression line, which we fit through the measurement data points collected during the coheating test. A disadvantage of this method is that we have to make quite a lot of assumptions on the solar aperture coefficient, which is indicated as A in this equation. And we will return to this with the other methods. So the second option, and it is also a simple linear regression. This we obtain when we divide all of the terms in the equation left by delta t. So this way we obtain the equation on the right on top of the graph. The advantage of this is that we can also visualize the method in a two-dimensional fashion. And we can, and on top of that, moreover, we can estimate both the heat loss coefficient and also the solar aperture coefficient as a part of the linear regression. So you can see on the graph that the heat loss coefficient is depicted as or is seen to be the intercept of the regression line with the y-axis. And the solar aperture coefficient is determined as the downward slope of the same regression line. A disadvantage of this method is that it gets quite unstable when delta t, so the temperature difference inside-outside, reach or approaches 0. So then the terms on the left and on the far right either become very high or become very low, making the method unstable in those conditions. Then the last option which presents itself is applying multiple linear regression. So here we we plot the data points in a three-dimensional space, which is seen here on the right. The disadvantage of this method is that it is not so easy to conclude anything from this graph. So we cannot, for example, read the heat loss coefficient as a slope of the graph. But we will zoom into this and we'll propose a method to still use the multiple linear regression, but we propose here a two-dimensional variant of this. So on the left you see again the three-dimensional scatter plot with a three-dimensional surface fitted through this using linear regression. And on the right you see an outline plot of the same scatter points and of the same 3D surface. So you see the thick red line indicates the intersect of the 3D surface with the QH delta T plane. And from this we see a layered flag hanging downwards. The layers in this flag indicate the discrete values of the daily averaged values of the solar radiation occurring during the coheating test. The advantage of this method is that we can read from the graph the heat loss coefficient as the upward slope of the regression line. Additionally, we can also conclude something about the solar aperture coefficient as the fraction of the traversed heating power and the traversed solar radiation by looking at the outline plot. A short note on the reliability of the coheating test. We've identified 4 factors which influence this coheating test. First, there is the duration of the experiment. It is quite clear that when we have more measurement data available, we will be able to have a more reliable estimate of the heat loss coefficient. A second factor are the weather conditions. For example, it is clear, we've seen that experiments which are performed in winter are more likely to yield better results or more accurate results than measurements or experiments which are performed in summer. Test case, we see that, or it is clear that some buildings are just more easily assessed than others. And the last factor which is important here is the analysis method. So which model are we trying to fit to our measurement data proves to be important here. Let's fix the last 2 factors and look at the influence of the duration of the experiment and the weather conditions during the experiment. So we will be looking at a simulated test case. So we've simulated the coheating test during a whole year. So we have 1 year worth of data of a coheating test performed on a simulated test case. We can look at a certain part of the test, which has so we have a certain window on this 1 year worth of data with a specific duration and a specific start date. What we can now do is we can vary both the duration and the start date. So we can, for example, consider longer experiments or shorter experiments, but we can also consider different start dates for the experiment. So we can choose to perform a 3-week experiment, for example, in winter, but we can just as well choose to perform it in summer. The next graph shows the results of varying these 2 factors. On the y-axis we have the assessment result, and on the x-axis we have the duration of the experiment. In the middle we have indicated the target value, so we are lucky, we have a simulated test case, so we know what we want to obtain as a result of the coheating test. The graph is a collection of scatter points, and it's actually the heat loss coefficient which results from fitting the equation which you find here to the measurement data, the daily average measurement data of the coheating test. You see that the scatter points are colored in different colors, and this actually reflects the weather conditions during these different experiments which are collected here. Red color indicates that on average the heating power was rather high, and the blue colors indicate that the heating power to the indoor environment was rather low during that experiment. The average heating power is a direct indicator of the temperature difference inside-outside during the test, and also the solar radiation. So a high average heating power essentially means that on average we had a high delta T, so on average the outdoor temperature was low, and on average we have a rather low solar radiation. So to summarize, The red points indicate experiments that were probably performed in winter, and the blue points are more likely performed in summer. But to go to, so this graph actually shows the reliability of the test. So for example, if you look at a duration of 50 days, we see that we get, when we apply this method, we get a quite a large spread around the target value. So we will need to adapt our method to obtain reliable results more rapidly. So the next graph shows you the result of applying a more complex model to the data. So in comparison with the previous model, we've forced the regression line through 0. We've only considered winter data, so on average we have a high mean heating power. We've also included the influence of solar radiation, and we've also included the influence of thermal lag. So we see that when taking these considerations into account, we see that we get a far more reliable result on the basis of shorter experiment times, durations. So here we see that even for example, a 10-day experiment, we get quite reliable results and very close or on the target value. So concluding, it's important to choose the appropriate analysis method, to choose the appropriate model to fit to our data. We also have to extend the experiment for a sufficient duration, but we've seen that for when we choose appropriate analysis method, we should suffice with a measurement duration of 1 to 2 weeks. And it is important to select winter as the time to perform the coheating test. I will quickly go through the test case, which we've performed 1.5 years ago. It is a terraced house in Herstal, Belgium, which here you see the front facade. Here you see the garden facade. It has a nicely south-oriented garden facade. The nice thing about this test case is that we've performed, during the coheating test, we've performed 2 renovation steps. So this allowed us to assess the actual obtained improvement of the thermal performance of the building fabric. The coheating test was performed from February until May, so we have 3 months of coheating measurement data. I will quickly go through the measurement setup. So you've seen this already. In addition, we also placed some heat flux and surface temperature sensors to get a better assessment of the thermal performance improvement of the different components. We also did blower door measurements and tracer gas tests to better assess to better decouple the transmission and ventilation heat loss, which are grouped into the overall heat loss coefficient, which we determine as a part of the coheating test. So 2 renovation steps were performed, and today we will only consider the first step. So we've blown in insulation into the facade and party wall cavities, and in addition we've insulated the attic floor slab. So here you see images of where they are insulating the cavity wall. The outside wall cavities are also insulated, and we've also insulated the attic floor. Here you see the measurement data which is collected before and after this first renovation step. So we are also only looking at the first 2 columns. And you see here clearly the difference between the 5-minute data which we collect during the test and the daily averages which we use as a basis for the analysis. So you see the daily averages in a thick red line. These are the results of applying the coheating test analysis. So it is important to distinguish between the 4 columns. The 4 columns are the results of applying or assuming different models or fitting different models to the measurement data. On the far left, for example, you see that we've only took into account the temperature difference inside-outside, and we've not forced the intercept through 0, whereas on the far right, we've included the influence of temperature difference, solar radiation. We've also forced the intercept of the regression line through 0, and we've taken into account the thermal lag effect introduced by the building fabric. The most important thing here is that the coheating test proves to be a very useful method to quantitatively show the final thermal performance improvement of renovation steps. So we clearly see the decreasing slope before and after performing or placing the installation. From the two graphs on the right, we conclude that we have improved the heat loss coefficient with about 110 watts per Kelvin. So conclusions: the coheating test is a viable method to assess the thermal performance of buildings. It is essentially based on a stationary analysis of a quasi-stationary test. So this means that the models which we fit to our measurement data is essentially limited in complexity, but it still offers us the opportunity to estimate the overall heat loss coefficient of the dwelling. We've identified some of the underlying physical phenomena which work behind the scenes of this simplified heat balance. We've proposed a way to visualize the multiple linear regression in a two-dimensional fashion. We've also talked shortly on the reliability of the coheating test, where we saw that given the right assumptions and given sufficient duration of the experiment, we can be confident that we will obtain a reliable result. And we've also shown that the coheating test is a nice way to show the renovation-induced performance improvement of the heat loss coefficient. Thank you for your attention, and if you have any questions, I will be happy to address them.